going to have to find a better way of cleaning this damn board, because this way at the moment is not working. So the next lecture, after going to the supermarket, I will find a solution that is better than this one, because this one is not working. Frustrating, annoying. So I'll have to do some experimentation and improve it. Okay, so if you have two statements, two mathematical statements. For example, here's an example of one: a squared is even. That's a statement. Call it p. You have another statement, mathematical statement: a is even. Call it statement q. So if p and q are mathematical statements, and if from p you can deduce q, and from q you can deduce p. If you can prove both ways, from the left-hand side you get the right-hand side, and from the right-hand side you can prove the left-hand side. If you can go both ways, so if and only if, then p and q are said to be equivalent. Okay? So two equivalent statements, they're essentially the same thing. You can deduce the other from one, and you can deduce the one from the other. Right? So equivalent statements. Now, this if and only if can be expressed in a similar way, using different words, and it's of the form NSC, meaning necessary and sufficient condition. Now, I'll rewrite that. It's somewhat similar to if and only if. Okay, so let's say P is a necessary condition for Q. Right? So you have to have P to get Q. Right? For example, to let Q be to get into university. Right? Now, a necessary condition, P, would be that you pass the entrance exam. Okay? So a necessary condition to get into university, that's Q, is P. P is you pass the entrance exam. Right? So what can you deduce from that? Well, if Q is true, if you got into university, you must have passed the entrance exam, right? So P. So if P is a necessary condition for Q, then if Q is true, then P is necessary. Okay, so that one. Now, here's the other one. The other P is a sufficient, like as enough. So is a sufficient condition for Q. So what would be a good example? Sufficient. So it's enough. So so P is enough to get Q. So if you have P, you can get Q, right? So if P is true, you can get Q. So a necessary condition, you write it this way. And if it's a sufficient condition, you write it that way. So this is an alternative way of expressing like the IFF, if and only if. It's just an alternative way. And so if we wanted to write the necessary part of the proof. Now, so if you're given a theorem that P is a necessary and sufficient condition for Q, and you're asked to prove that, again, you have to prove it both ways, right? So in effect, you have to make two proofs. And so if you start with a necessary condition, then you would have to prove if Q, then P. And sufficient, you go the other way. So you'd have to prove if P, then Q. Okay, so they're sort of equivalent, similar. They're just using different words. But they're essentially the same. So the IFF, if and only if, and the necessary and sufficient condition are much the same kind of thing. Right, now I've mentioned this a little bit before, and I'll finish off here with just a few examples. How do you disprove something? How do you show that something is not the case? Well, it's sort of much easier, well, usually easier than proving that of a normal proof. In a proof, you have to show that something is true for all cases, right? You have to cover all bases. Now, to prove that something is false, all you have to do is just find one counterexample, one example where the thing you're trying to prove is not true. And that counterexample disproves your hypothesis, your conjecture. Okay? So all you have to do is just find one example where what it is that you're trying to show is false. You show that it's false. So, and that example is called a counterexample. Right? Counterexample. Let's do a few examples. Well, I've done it a bit earlier. Like, all primes are odd numbers. Now, that's true in all cases except one. Right? Now, there are an infinite number of primes, so that generalization, that suspicion that all primes are odd numbers, you think would probably be true, because 3, 5, 7, 11, 13, all the primes, from starting at 3 upwards, they're all odd numbers. Right? But the very first prime is 2, which is an even number. And that contradicts your assertion, right? That all primes are odd. So you found your one counterexample, 2. The prime number 2. That's not odd, and that's sufficient to kill the assertion, the idea, the hypothesis, the conjecture, or whatever, that all primes are odd. Now, how about the reverse? Here's another conjecture, another possibility, some idea you're trying to prove or disprove. All odd numbers are prime. Right? All odd numbers are prime. Now, can you find... sorry, when I say numbers, I'm talking about integers. Okay. Well, let's say natural numbers, in fact. 1, 2, 3. So can you find can you think of an odd number that is not a prime? So 3, 5, 7. These are all primes. 9. That's not a prime, right? Because you can divide it by 3. It has a factor of 3. 3 squared is 9. So 9 is an odd number, but it's not a prime. Right? And your assertion, your conjecture, your hypothesis is that all odd numbers are prime. Well, we've found a contradiction, a counterexample, therefore that's not true, right? So it's false. So to disprove something, you only have to find one counterexample, and we've done it here, 9. That disproves it. Okay, something a little bit harder. Some proofs some proofs are not easy. So let's try this one. Now here's your hypothesis: n squared plus n plus 41 is prime. Okay? That's your hypothesis. True or false? Now, can you think of a value of n where this is false? Can you find a counterexample? Well, you may have to think a bit. It's not immediately obvious. Well, perhaps to some of you. Well, I'll just give you the answer. Let n be 41. Okay? So you'll have 41 squared plus 41 plus 41. Now you have 41 in common, so that's 41 times 41 plus 1 plus 1. Okay? So that's 41 times 43. Now 43 is a prime number, and so is 41. But look, you have two factors. Therefore, this is not a prime when n is 41. Because when n is 41, well, let's call this, what do we call it? G. Right? So by definition, so this integer g here is not a prime when n is 41. Because when n is 41, g is 41 times 43. Okay? So g now has two factors of primes. So you can divide g by a prime number other than itself. Therefore, by definition, g is not a prime. So this is false. Okay? You found a counterexample, n is 41, so g is not a prime. Right, well, that's the end of the first lecture. Almost. Now I will have another part, and this is sort of typical probably of every lecture I will give, more or less. At the end of the theory part, so this is the end of the theory part of the lecture, and at the end I will solve some actual problems to help you, think about using the theory. So the next part of this lecture will be me taking some problems from the textbook, and I'll solve about a third or a half of them, I guess, to give you a feel of how to use this theory with some problems. So the next part will be problem solving.